Alright, let's go ahead and try to understand what is the activation function. But before that, let me show you where we mentioned activation function. At the start of this lecture series, I told you here there is the activation function, which is also referred here as the step function here. So this step function or the activation function which is shown here, this is actually described in this lecture. So this activation function is kind of a function which actually transforms a signal non-linearly. So suppose that you are given an input x. Based on the value of x, let's say if you are using activation function as the sigmoid, then based on the value of the x, alright, so x is 0, so at that particular time, the activation function value will be 0.5. But as soon as it goes into the positive direction, the value of x, then it starts giving the output here at the higher end. But in case of the step function, it was completely something like this. So it was either 0 or 1. But in case of the sigmoid function, it is not that case. So these values are actually varying between 0 to +1 here, depending on the input value x, or you can say that not just input value x, in fact, depending on the input value x and multiplied by this weight, and then there is bias term here which is added there. So based on these values, when all of these values are actually summed together, then this activation function is applied. So after doing all those calculations, so based on that value, this final output is decided. When let's suppose that if value is 0, then final output will be exactly 0.5. When it is greater than 0, then the value will be greater than 0.5. On given condition, this function is applied there as the activation function. There is another type of the activation function, which is the tanh activation function. So this tanh activation function is something like this. So the problem was with this sigmoid function that its value actually limiting from 0 to 1 only. But that problem is removed by the tanh so that your model learns faster than the sigmoid function. So the output changes from the -1 to +1 in case of the tanh activation function. There is another activation function which is known as a ReLU. So this ReLU activation function is like the max of 0 and x. Whenever your value is less than 0, then it is always 0. But when it is greater than 0, then the output will be equal to value. For example, if we go back here to our threshold unit, linear threshold unit, suppose that your input is multiplied by weight and its value is coming negative, and we applied their ReLU function, then in that case, for a negative value, output will be 0. But when this value is positive after adding these bias term, then we can say that whatever the value is coming, on given condition that the activation function is ReLU, then the output will be the exactly same. So that's what we are seeing here. It says that the maximum of 0 or x. So when x is negative, obviously in that case 0 is the maximum. When x is positive, then obviously the x will be maximum. That's why in this activation function, if you see there, when your value input x is, when I say the x, it is not exactly the input x. So it is x multiplied by its weight plus the bias, right? So this x is actually just before, this x is the value just before the activation function. Alright, so this x, when this x is greater than 0, then it is just following the output there. Alright, this output is just following the x there. There is another type of the algorithm. This is the leaky ReLU algorithm. So what was the problem with this? The problem was when the value is negative, then the output was becoming 0. So that was creating a problem during the deep learning model learning. So just to avoid that problem, a leaky ReLU is developed. So this type of the algorithm gives you a very small output so that you can get the gradient, so that you can get the learning of your deep learning model, even when your output your input to the activation function is negative. Alright, so you see there is a small difference. it is 0, but this one is not the 0. There is just a small number there, 0.1x there. Then there is the max out function. So it has the weight, the transpose of the weight 1 plus this is the bias, and the transpose of the weight 2 and plus bias 2. So it's something like that, where the two outputs are, two inputs are, two weights are there, and then it multiply by the input and then the biases and then take the maximum whatever the comes there. It's something like, let's say the two input is coming, something like this, the two input is coming and then the weight is getting multiplied, or you can say that, yeah, that is not shown here seems like, but maybe we can see something like this. There is one input and let's say the multiple weights are there, then it is taking the maximum of those weights whichever it comes there. And then there is the ELU. So this ELU is kind of the similar thing what we had seen here as a leaky ReLU, but the only difference, if you see there, leaky ReLU have here a sudden change at the origin, similar to here and here. So the ReLU and the leaky ReLU is not differentiable at the 0. So this becomes here a smooth point when you use their ELU. So ELU make it here a smooth point. So it make it here a differentiable when it is at 0 or any other region. So whatever these domains are there or the regions, it is differentiable to all these regions. So there are less chances that your differentiation will be unstable. So it's very less chances there. All right, perfect. So this is all about activation function. I'll see you in next lesson.